Stevens with Pipeline Plastics. And Steven, if you wouldn't mind coming on, I'd appreciate that at this point. And tell us a little bit about who you are and what you do.
Sure. Thanks, Peter. Appreciate the introduction. So I'm Stephen Boris. I'm Vice President of Engineering at Pipeline Plastics. We're a major polyethylene pipe manufacturer in the United States. Been in polyethylene pipe for 30 plus years. I just say the plus now after 30. And been in all aspects of it. And I'm very excited about the time we're at in our industry with everything we have going on and the growth that we're seeing and the problems that we're solving with today's infrastructure. So it's great.
Well, speaking of problems, you have a new background, Stephen. Tell us about that.
Yeah, so this is just a screenshot of 50,000 feet of polyethylene pipe, 24-inch, that was shipped up to Oklahoma, southeastern Oklahoma. So the mayor of the town there in Tishomingo, Oklahoma, had a economic growth and vision for that area. And one thing they were lacking for that was water. So they were able to work with multiple agencies. So they had an Indian agency for the Indian tribe located there. They had local agencies. They had state agencies from the state of Oklahoma and federal. They're able to get all of those to contribute funds to fund a 50,000 foot run from a new water well from the aquifer that was outside of town to a treatment plant so they could get all of this new economic growth potential for Murray State College and their hospitality group, potentially for a new Indian casino and hotel, all sorts of things that would not be possible without the resource such as just clean water.
Yeah, my well quit working last weekend, Stephen. I got home and my wife said, well, I'm sure glad you're home, but guess what? There's no water. Until you don't have it, you don't realize how important water is. And certainly economic development is not going to work without water.
Right.
Okay, with that, I want to thank my bench. So what's our bench? Alan Ambler, come on. Our bench is those experts that are sitting there waiting for your questions. Please use the Q&A. Alan Ambler, welcome.
Hey, Pete. So if you've attended our webinars before, you know that we've got a group of people, these fellows that you're looking at here, that are going to answer your question as you type it, and hopefully that'll spur even more questions. So definitely write us your questions. We're here to support anything that's very topical to what Stephen's talking about or the webinar content. We could very well choose to answer that live as we go through. So definitely happy to be here, Pete. Happy to see all of Stephen's pipe that he's showing us there, and love to share about projects. That's one of my favorite thing to do, is to hear about infrastructure all over the country. So definitely share that information with us.
Thank you, Alan Ambler. Stephen, let's start. I'll turn it over to you, but let's start with, who is the Plastics Pipe Institute? How are they different than the Alliance? And what role do they play? And I'll turn it over to you.
Thanks. Let me share my screen with you here, and we'll get going. See if I can figure out the technology today.
You got it.
Did it come up?
Yeah, you got to pick the other screen. You're on, it's showing Zoom right now.
Sorry about that. I thought I picked screen 2. All that practice and it still didn't work.
Well, that's why they don't let me do it anymore, because I can't figure out the difference between screen 1 and screen 2. All right, Alan, could you come on, and while he's figuring that out, could you tell us a little bit about the Plastics Pipe Institute?
You bet. So the Plastic Pipe Institute is a group that studies all plastic pipe or plastics in general, and then produces great references and resources for us to be able to navigate through designing with that plastic material. And that was just timely enough for Stephen to be able to take it away here, Stephen.
There we go.
All right.
Thanks, guys. I think I got it now. So let's start with the Plastics Pipe Institute top 10 resources. these are ones we picked that we thought would be the most of interest. And you have to remember there are dozens of resources available through the PE Alliance as well as the Plastics Pipe Institute. So I think one of the main resources that everybody needs to be familiar with if you're going to deal with polyethylene pipe is the Handbook of Polyethylene Pipe. So this is literally a culmination of probably 50 years of experience that was put together by various experts around the country over all these years. It started out as individual reports, individual notes, individual documents. And then over time, we said, hey, we got a lot of these things. Let's put them into a manual. And so this is the be all end all of polyethylene pipe. It covers every application, every aspect of the material, of shipping and handling, the manufacturing, design of different types of applications, burial, marine environment, geothermal, all of it. So this is a great resource. And what's nice about it, it's available for free download. Every chapter is available as a PDF download from the Plastics Pipe Institute website, plasticpipe.org. Or if you're like me and you still like a book, you can order a hardback copy of this book at a very low price and have that on your shelf for review. So anyway, this is a great resource to go to. It's kind of like a textbook. It goes through, gives you all the background and information, and then gives you examples of how to apply it.
So we charge $60 for the book. And I think that's the same thing PPI. I just buy 12 of them at a time and we ship it out to you. So that is available for that cost.
Right. Yeah, I say it's not a great cost, or like I said, if you just want to do the PDF versions, you can do that as for free. And there's a lot more on there too. So there's calculators, there's software, installation guides, technical notes, as well as technical reports that have been developed over the years. It's kind of an archive place. Hundreds and hundreds of case studies are available on both the PPI website as well as the PE Alliance website. And then installation practices and guides such as electrofusion and things like that. We'll go through a few of those. So today, the scope of the presentation is going to cover more or less like the specification. How do I specify polyethylene pipe for a water wastewater project? And then it'll go into some design aspects of that. We'll cover some installation and then some maintenance type things if you need to, such as squeeze off, joining, different things like that. And then we'll get into specific topics from the PE Pipe Handbook. And well, it'll be outside what's in the PE Pipe Handbook specifically, or the field manual for municipal applications, which again is available on the website for free download. So let's get into it. So the first document, and this is really getting into the base of where polyethylene pipe or polyethylene compounds that are used for pipe comes from. The polyethylene that is used to make pressure pipe is an extremely engineered type polyethylene. It's not the same type polyethylene that you use for your trash bags, which is low density, very stretchy. It's not the same type of polyethylene that your 1 gallon milk jug is made from, which again is polyethylene. It's not the same as your bleach bottle. Again, there's hundreds of types. The type of polyethylene used to make pressure pipe is a highly engineered compound specifically for this application. So it goes through a lot of testing, a lot of analysis and verification of its long-term performance properties, short-term and long-term, to verify it can be used in a long-term durable application such as pipe. Each compound is then listed by the Plastics Pipe Institute in a document called PPI's Technical Report 4, or TR4. It lists the hydrostatic design basis, hydrostatic design stress, and MRS, if it has one, of those listed materials. So it's a great resource to go to see, all right, does my pipe manufacturer, is he using a material that's listed in PPI TR4? That means it's gone through this analysis. Let me show you a sample of what it would go through. It's gone through all of this, probably about 2 years is about the minimum time it takes to get this data put together. So to have multiple lots of material that has to go through this, what's called a stress regression analysis to see, all right, let me put pipes on test. All of these little X's represent a failed piece of pipe on at a certain pressure or a certain stress level. And then you see how long it takes before it fails. Now, this is on a log-log scale, so it looks like it's very linear. When in fact, if you put it on Cartesian coordinates, it's very logarithmic. So it starts out and it kind of goes like this, and then it becomes asymptotic very quickly, so you can then forecast a very long points in time. So you understand here, this is 1 year here, where this is 50 years here, and this is over 100 years here. So you can see just this region, it becomes pretty flat. So this is how we determine what is the long-term HDS, or hydrostatic design stress, that this material can be used at. And the definition of HDS is a stress level with high probability that failure will not occur. So that's where we start from our calculation about how we get from a stress in the material to how we get to a pressure rating for the pipe.
Alan, you got something to add?
Yeah, I was just waiting for the natural pause. Good job. This is sorry, Stephen. This is one of my favorite graphs. So I just couldn't keep my mouth shut because exactly what you're explaining. So what's behind all of this, if I'm correct, is lots of vats of pipe where they're putting it through all of these motions and really validating that the resin that you guys have created into a pipe can satisfy this. And then not only that, but you're conservative in the difference between that design factor as well. So there's more conservatancy even before we get that pipe into the field. Is that correct?
Absolutely, that is correct, because we get that question a lot. Say, oh, this pipe has a certain pressure rating, but I don't want to go up to that pressure rating. I want to derate it even further and be more conservative. But Alan, you're absolutely correct. So when we establish the long-term strength of a material, it's way up here at 100,000 hours, right? And even further out in time beyond that. We take a design factor, which reduces that stress from the hydrostatic design basis all the way down to the hydrostatic design stress. That's the maximum stress of that pressure rating that pressure rating will induce on that pressure vessel or that pipe. So there's a lot of conservatism, how about that, built into this pressure rating of the pipe. It's just a basic thin wall pressure vessel equation that takes the stress at the mid wall of the pipe. And then you can add different temperature factors and surface factors into that. But this is for 73 degrees in a water environment. This is a long-term strength that the pipe or the material can handle. So when you go to PPI TR4 and you go up and look something like PE 4710 materials, you'll see listings of what's called dependent listings under pipe manufacturers. And each pipe manufacturer will have compounds that they're approved. They've gone through an evaluation process that shows they can reproduce these compounds that have the PE 4710 designation and utilize those to make pipe with. And so if you want to approve your pipe manufacturer, you can go in and take a look and make sure or have a requirement in your specification that your pipe manufacturer must have a listing in TR4. That means it's another level of scrutiny that's been put on that product, that they're using the right materials for the right application. Now, it's interesting to point out, I'm just showing polyethylene here, but every thermoplastic material goes through the same process that's used in North America. That goes for PVC. Every PVC compound is used. It's also listed in this document. Polyamide materials, CPVC for hot water applications, cross-linked polyethylene for hot and cold plumbing applications. They all go through this exact same evaluation process and are listed within TR4. That's how important this document is to our industry. The next document is going to be coming from the PPI's Municipal Advisory Board, or MAB. So that's an independent group of municipal engineers, contractors, university professors, like I said, design engineers, and other experts from the industry that say, all right, what information do we need for municipal applications specifically? So they say, well, the first thing we need is a model spec. So you got to know how to specify polyethylene for a potable water service, distribution, or transmission system. So this document was actually just updated in 2024 and republished. So this is the best, latest, and greatest information on how to specify all aspects dealing with polyethylene pipe for water applications. How to specify the material, how to specify the pipe manufacturer, how you're going to join it, how you need to be qualified to join it, how you need to store it, ship it. It goes through all of those aspects. So you don't have to start from scratch as a design engineer or an owner that wants to specify this. This is a great template that'll give you 95% of everything you need for your project, and then you can take it and customize it for your specific application. So it covers, how are you going to do the installation? How are you going to reference AWWA M55, which we'll talk about later for burial and backfill. So it goes through all of those things so you don't have to research all that yourself. So some of the things you'll see in the model spec, so it's going to specify the types of material, PE 4710 pressure classes. You can see here for the larger diameter, C906, which covers 4-inch through 65-inch pipe. You have DR17, DR13.5, DR11, and DR9 are all allowed within this document. So that gives you a pressure class rating from 250 PSI at the heavy wall DR9 all the way down to 125 PSI, working pressure rating, surge is on top of that. We'll talk about that later, for a DR17. So you have allowable surge for that DR17s at 188 PSI, and your occasional surge is all the way up to 2 times the pressure class, 250 PSI. Now, the one thing to note here, though, is that for AWWA C901, which is for small diameter water service lines, 1/2 inch through 3-inch, for water service lines, C901 now only recognizes DR9 for that application. Because it is such a rigorous application, this covers all installation and burial and usage aspects for a service application, because we know it's not going to be buried with the same amount of rigor and care that a distribution or transmission line would. It's going to be a shallower bury mainly, usually 12 inches or less. Not always, but can be. And so a DR9 will give you more robustness for that product to assure that you still have that 100-year design life. It's interesting to note here also for design what is recommended. So for normal flow, 4 feet per second, the average that we see around the country is 6.7 feet per second. So 4 foot per second average flow or normal flow is not uncommon. In fact, that's what's recommended. 8 feet per second for occasional flow. So all that needs to be taken into account in your designs. And then also for 55 cycles per day. And all that comes together to give you a 100-year design life for fatigue and for usage. Now, that's going to be key because you don't want a 100-year estimation or it might last 100 years. This is going to take all the aspects of polyethylene pipe and say, I'm going to get a 100-year design life for this product. It gives you the material specification they're going to use for large diameter, 4-inch through 65-inch. You want that made and manufactured according to AWWA C906. You will probably want it NSF certified for potable water applications. So the toxicology aspects of it would be NSF 61. You might see pipe labeled also NSF 14. NSF 14 means it has been certified not just for standard 61 for potable water contact, but it's also been certified and tested to conform to C906 as well. So that gives you another level of scrutiny that you have on this product. Minimal cell classification, PE 445574C. If you go to ASTM D3350, we'll spell out all those properties. And the CC3, or the chlorine categorization resistance number that the material has been tested to. CC3 is the highest rating that you can get for polyethylene material. Again, will give you that 100-year design life against disinfectants in every situation that you're dealing with in the United States. So again, all that's in here. You don't have to research it and figure it out yourself. It's all laid out for you. It talks about installation practices. So for installation, you're going to have pullback limits, you're going to have burial, different things like that. So here's just an instance, or safe pull loads on polyethylene pipe. Get that question a lot. How much force can I put on this polyethylene pipe? Safe pull stress is going to be much less than the maximum tensile yield stress of the material. So let's say you want to just pull on it for an hour or less. you can go up to 1400 PSI. Remember, the tensile yield stress on this material is about 3500 PSI, maybe even up to 4000 PSI. So you have a lot of margin of safety there that you're working with, so you won't damage the product when you're pulling it into place in certain types of applications. Hey, Peter.
Hey, Stephen, we just had a question that is Doug is answering, but it was phrased like this. It said, so how does velocity affect the fatigue life of polyethylene? So fatigue is something that's an issue for PVC, but does fatigue, is that a thing for polyethylene?
That's a great question. So velocity does affect it. And let me go back a slide here real quick. And I kind of went over this quickly, but this is an important point. So yeah, fatigue is ultimately how many types of pipes will fail. They're going to fail from corrosion if they're metallic. They're going to fail from fatigue. Some metallic and thermoplastic materials can fail by cyclic fatigue. And they're going to fail by maybe soil movement or rock impingement, something like that. So if you design for all of those factors to give you a 100-year life, then you're going to have a 100-year design life for that product. So the thing about polyethylene, you have to remember, it has surge capacity because it's ductile on top of its pressure class. Not all materials have that. And pressure class means something different for every material. So just because you have a ductile iron with a certain pressure class, PVC with a certain pressure class, you don't match pressure classes when you design with polyethylene. You have to design it for its individual performance. So surge will be what causes the cyclic fatigue. So anytime you have a water hammer effect, let's say at 8 feet per second, you're going to have a surge or a fatigue event built into that. If it happens 55 times a day plus, like say for a force main, that's going to be millions of cycles over 100 years. Polyethylene has been tested for 10 million plus cycles with full cyclic fatigue from full pressure class to double the pressure class. Not just starting with a pressure class of say 125 and testing it at 80 psi like it's going to be used. We tested at 125 and then double that to 250 and go through millions of cycles to make sure ductile fatigue will not be an issue for polyethylene. Great question.
Thank you.
Real quickly, just to flange this up here. So also on trenchless installations, there's some other documents you can go to, ASTM F1962, which is for MAXI horizontal directional drilling guidance. Or you can also go to PPI's Boraid, which is a soft online software, which will give you directional drill protocols and designs so you can get a first look at how that directional drill is going to look. What sizes do I need to use? What angles can I use? What depth do I need to go to? Different things like that. And then HDPE app is the design software that pretty much covers everything in the PE pipe handbook is covered in real-time calculations online at these URLs for the PPI handbook and design. So another thing we see a lot about is blocking, anchor blocking, and how do you restrain polyethylene pipe? So first of all, know that it's very easy to restrain polyethylene pipe because it has a lower modulus than other materials. The resulting force from any type of let's just say thermal cycling event or anything like that, or soil movement, the amount of force generated by the polyethylene is going to be much, much smaller than it will be for that same event on a metallic pipe such as ductile iron or even PVC. So you have to look at it individually. So there was a new study just put out by Cornell University that was sponsored by the Plastics Pipe Institute. And they looked at all the aspects of a buried pipe design that we didn't take into account before, and then came up with new anchor block sizing requirements. And all this will be put into the PE pipe handbook when it's designed, but it's already included into the HTTP app software online. So if you want to take a look at that. So let me go back real quick. So what it did, and this last bullet point is really what the crux of it is. It said, all right, let's look at soil restraint. Let's look at temperatures. Let's look at what really happens to this system when it's buried in the ground. And what it did is it essentially took the old design of anchor blocks and cut those in about a third of what they would have been in the past. Now that this is a properly designed restraint system, or restraint analysis, if you will, and can then put proper thrust blocks in place and how I designed those thrust blocks. So some of the things it did.
Let me interject a bit.
Oh,
So
you bet.
all polyethylene itself, once we get to that fusion joint, that is a self-restrained joint. So we are only really looking at anchor blocks for HDPE pipe when we are connecting to other materials or valves or other things like that as we're designing these. Isn't that correct, Stephen?
Oh, absolutely. Yeah, I didn't even mention that point, but you're exactly right. You don't really need them very often. The only time you need an anchor block to restrain any type of movement is when you're connecting to an appurtenance, such as a valve going through a wall, if you will, into a reservoir or whatever it might be, and you need to restrain the polyethylene from movement. Each individual joint is going to be fully restrained if it's heat fused, and there is no need to anchor that in any way. So it really reduces the amount of blocking that you need overall. So this new design, as you can see an example here from the HTPE app software, it gives you for a certain situation, 24-inch pipe, DR17, what does my block dimensions need to look like? How much reinforcement do I need? So it takes all of these things into account with the Poisson's forces and ratios that it didn't before to give you a proper anchor block design that'll work to make sure that if you are hooking up to a valve body that you don't want to have move in any way, it'll make sure that it can restrain that and it won't be an issue. The other document, which again was updated, I think this was updated maybe 2 years ago now, is the AWWA M55 Design and Installation Manual for Polyethylene Pipe. This is a great resource. So this is strictly focused on municipal applications, and it has 11 chapters, all dealing with engineering properties of the material, how you come up with the different working pressure ratings and pressure classes and surges, surge capacities for these different pipes. External loads, chapter 5 was all redone by Amster Howard recently to make sure everybody's using the same terminology and the same type of compaction requirements, same type of soil requirements for that flexible pipe design interaction that you have to have with any flexible pipe design, which is ductile iron, PVC, corrugated metal, polyethylene. All of those use the exact same design practice, which is a pipe soil interactive design to make sure you get properly compacted soils to give you a nice round pipe and not overly deflect the pipe during installation or during use. So all that's been revised to give you the latest and greatest joining and fittings that are available. There's been a big change in the fittings available in the last 7 or 8 years with all the different types of mechanical fittings available, electrofusion fittings, MJ adapters, flange adapters. It talks about all of those. Installation practices, maintenance and repair. That's a great chapter that people need to be aware of. If the pipe ever gets damaged and needs to be repaired, there's very easy ways to do it. The neat thing that's also included here is the Appendix B. That's all brand new. That gives you earthquake design applications. What's neat about that is polyethylene is inherently earthquake resistant because of its ductility and its fully restrained joints, as we talked about earlier. If you have a fully restrained system and a ductile system, it's going to be by nature earthquake resistant. And there's many, many real life situations that have been studied around the world during major earthquake events in Japan, Chile, New Zealand, that show that polyethylene piping systems have no failures during these massive earthquake events where you really need your infrastructure to maintain its integrity. We talked a little bit about, I think you heard from Dan earlier about the engineering package that's available. That's a great resource. It's a great compendium of all the different types of documents that you might need for a municipal application. Covers design, specifying, installing, and operating polyethylene piping systems. Everything we're talking about today is going to be included in that. We've talked about a few things already, the model spec, the MAB contacts. We'll talk about the rest of these here in a minute. But it's a great resource. Again, if you want that, contact Dan Landy afterwards or in the survey, and he'll ship you off the engineer's package, which has all of this information contained within it. Material and handling guide is very important for any pipe that you might have. How do I handle it? So polyethylene might be a little bit different. For one thing, it's going to be lighter than a lot of the piping products you're used to handling. But it still needs substantial equipment to handle it, and it has to be handled in the right way. So there's a PPI material handling guide for pipe and fittings. It was published in 2018. It's available on the website. And it's going to talk about how do I unload the pipe? What do I look at when it gets to the job site? What type of equipment do I need? Is it going to be in links? Is it going to be in coils? Is it going to be in bundles? How do I do that? And again, like I said, the inspection of it when it gets to the job site is very important as well. You want to store it usually in a storage yard when it gets to the pipe before it's used on the project. And you need to cut it to length in certain cases. So there's going to talk about, the handling guide talks about many aspects of that. So you can see here, just as a quick example, this is a piece of 54 or 63-inch pipe, I believe, actually, out of one of our Texas plants. And you can see that it's recommended to lift polyethylene pipe with nylon straps. This makes sure that you don't damage it. You have a large enough back forklift or telehandler that can lift it properly. You have crew people out of the way, so the driver may not be able to see them. It takes into account. And then you're going to lift it and put it onto the truck and certain chocks and blocks to make sure it stays put. So that's just a few of the basic aspects that you want to look at for polyethylene. Here's one thing that you don't want to do when it gets to the job site. Let's take a look at this. This operator is very good at his job. You can see he's very good at lining up the bucket to make sure he's going to get what he needs to lift this pipe off the truck appropriately. He's taking great care and making sure he lines it up. And then once he is sure he's ready to go, he's going to unload this pipe in his own particular fashion. Now, that's what you don't want to do when you unload the pipe. The interesting thing about it is the pipe wasn't damaged, so it's okay, but a lot of safety aspects associated with this. And the truck driver actually took this video thinking, what is he going to do here? And so he knew something that was going to happen that he wanted to capture. So what do you have to say about this one, Alan?
Well, sometimes we do get lucky and find those videos that show exactly what not to do, and this is one of those. So the Alliance does spend a fair amount of time trying to find videos and definitely share it with us. So we've got about 30 minutes left, Stephen, and you've got probably about 50 slides. So we'll have to start that a little bit there, and hopefully Pete doesn't interrupt too much.
You bet. Keep it going. The inspection form is very important as well. So this is a great example. It comes out of MAB 6 for incoming pipe material inspection. So it just kind of makes sure that, okay, here's my project name, the inspector name. What am I getting? Am I actually getting on that truck before I unload it? Am I going to get everything I'm supposed to be getting on that truck? Is it the right size? Is it the right DR, a wall thickness? Is it made to the right specification? Does it have all the right markings on it for that I'm supposed to be getting? Check all these things before you unload it. That way, if there's an issue, maybe something wasn't shipped right or the pipe may have been damaged during shipment, you'll have all that documented before you unload it. And then it'll make it much easier to send that pipe back and be loaded the right way, or to replace damaged pipe and anything that what it might be than if you had to unload it and then try to load it back on the job site. Stacking heights as well. Polyethylene pipe you can stack. The larger diameters, though, it's recommended that you don't stack more than one high. Once you get up below 36 inch, you can stack it 2, 3, 4, even 10 high, as long as it's chocked properly and protected properly, or it's not going to fall off and roll over people. TN51 talks about butt fusion. Butt fusion is the number one heat fusion joining method for polyethylene. It doesn't require a fitting. It requires a fusion machine to align the pipe and bring it together in the right fashion. But once it's brought together and it's fused in this manner, it becomes a monolithic pipe piece at that point. There's no longer a joint that's going to come apart. Again, that joint is now as strong as the pipe. It's fully restrained, and it won't ever be a weak link that's going to be a problem within your piping system. So that's the number one way of doing it. There are mechanical options. There's electrofusion options, which we'll talk about. But this is the main thing that you'll use day in, day out. It's a very simple process, and TN51 just talks through the steps of that and gives you the right references of how you go about qualifying a fusion joiner for that process as well. So you can see here, the first step of that is to face the ends. You put the pipe into the fusion collets and you bring both ends together, and these blades spin slowly around it. And that gives you a nice, clean, uniform, parallel surfaces. So the pipe comes together in a nice, uniform manner. So this is the first step in the fusion process, and one of the probably most key parts of it as well. This is what happens during a butt fusion joint. So you can see here, this is the wall thickness. You can see the two ends were brought together, and it talks about the different aspects of it. So you get your external rollback bead and you get your internal rollback bead from the molten material that was squeezed out. And it gives you different flow profiles. You can see on the picture to the right here, which was a very unique piece of pipe that was made. I'm not sure if it was made on purpose or by accident, but it certainly gave a good graphic for this example. You can see that when the pipe ends are brought together in this fashion, the melt is extruded out this way, and that interface is right here in the middle, which you get that, what we call a co-crystallization zone, where you get that real entanglement that give you a fully strong joint. It's not just touching together or mechanical adhesion. This is a true intermolecular crystallization area that gives you a 100% strong joint. Again, the different aspects, if you want to see the details about what's really happening when the two ends come together, you have the melt zone, the radial flow, diversion, the melt beads. You can take a look at that. All that is included within this document as well. The next method of joining, which again is very popular if you can't move a piece or you have a specific situation, is electrofusion. Electrofusion couplers are very common. Electrofusion tees, tapping tees, saddles, whatever it might be. Electrofusion is an excellent alternative for that. So the Municipal Advisory Board has published 2 documents for that. You can see they did it very early on in their development. It was the first document they published was MAB1 and MAB2. One handles 12-inch and smaller polyethylene pipe, the steps to go through to make sure you get a good electrofusion joint. And then if you're doing larger diameter, 14-inch to 30-inch, it goes through the guidance about what you need to do, what you need to look for, steps you need to take to make sure you get a good joint. Why is this important? Because you have to go through the steps to make sure you're going to get that good joint. If you go through the steps, it's going to work every time. Very quickly, these are the steps. Cut the pipe ends. Clean the pipe ends. Can't stress this one enough. This is the first cleaning step. Mark the stab depth of your pipes. How deep does it need to go into that coupler? Then you're going to scrape it or peel the surface off. That's going to give you a nice clean surface that electrofusion coupling is going to bond to. And this is a very key part of that. Then you're going to make sure that when you stab it to the mark depth, that you're going deep enough to get full stab of those couplings on both sides. Then you're going to, if you need to, put it in rerounding clamps and alignment clamps to hold that in alignment, make sure the pipe's fully round and fully in alignment to go into that coupling. Connect it to the electrofusion box, press the button. It's going to go through its process because it's read the barcode of that fitting, so it knows exactly how much energy to put into it to join it the right way. and you're done. Isn't that about it, Peter? Or isn't that about it, Alan?
Yeah, yeah. So the key difference between electrofusion and butt fusion is there's a little bit more operator processing on the electrofusion, and both scenarios we're getting back to virgin resin. So exactly the same things that Stephen and his company would do at the extrusion facility when they're controlling virgin high-density polyethylene resin material to get it into a pipe. Even before it's delivered to your site, we're just doing the same exact thing to ensure the health of that fusion joint. So that definitely good steps to follow, Stephen. You're very succinct and specific. Love it. Keep
Yeah.
going.
Can't overemphasize the cleaning portion of this enough. That's what's going to give you a good joint. So if you can't do a butt fusion or electrofusion, you may need to do a flange adapter, right? So flange adapters are very common to flange up again to an appurtenance that you will be. Maybe it's a tank, maybe it's a valve, maybe it's a flow meter, whatever it might be. There are flange adapters available for that you can, what they call stub ends, that you fuse onto the polyethylene pipe, typically with a butt fusion. And then that allows you then to flange up to another appurtenance. So PPI's TN38 is how you go about doing that, and more importantly, how you go about torquing those bolts to make sure you get a nice, even compression of that flange adapter. So what you want the bolts to do, the bolts have to overcome the pressure, the surge, any type of thermodynamic or temperature contraction or expansion, any type of bending that might occur, flange alignment, and then whatever variance you want to take into account. The force in these bolts has to be greater than all these other forces trying to pull that apart. So once you go through that calculation, you can see that there's a certain torque value that you need to put on all these bolts to make sure that you get the right contact area and you get a fully sealed flange. Now, the nice thing about polyethylene is you don't have to use a polyethylene to polyethylene flange adapter joint. Does not even need to use a gasket as long as it's aligned properly and as long as the bolts are torqued properly. So this is just an example. So if you're doing less than 18-inch pipe, you do the 30-30 rule. So you're going to tighten it 30% of the recommended torque value. Then that's to seat it all. And then you're going to start with the star pattern. You're going to go to the first bolt and tighten an additional 30. Go around to all the bolts and do that. Then you're going to go back to bolt 1, tighten it the rest of the value. Now, the last step is you're going to let that sit for 4 to 24 hours for it to relax and get in its final state. And then you're going to come back and do one more final torque to that torque value again to fully seat everything and make sure that you have a nice tight joint. If you're going to do greater than 18-inch pipe, you do the exact same thing, except you go through one more step and you only start with 25% of the torque value, additional 25, and then the final value after, again, that 4 to 24 hour period to allow it to relax and creep a little bit, if you will, and make sure that you're going to have that final force where you have a joint, a flange that won't leak. If you are going to do butt fusions, which is, again, the predominant way of doing this, you're going to say, well, how do I know that that butt fusion was done properly? Well, there's a device out there called a data logger, and it records the pertinent key data information and parameters of that fusion joint. And if you can see this, you had a 99% chance that all those joints are going to be good. Now, I say 99% chance because the only thing that could possibly go wrong is if some dirt blew in there or something like that that wasn't taken into account. Then that's the only thing this type of data logger won't record. But everything else, as long as it goes through this process and you record the steps, you can be assured that you're going to have a good, strong joint afterwards. So this is what a typical graph from a data logger will look like. So this is pressure on the y-axis and time on the x-axis. So you're going to, first of all, the first few seconds of the fusion process, you're going to bead up. Now, what that means is you're going to bring those pipe ends together that you've already faced and got very clean and uniform and parallel to each other. So they're very symmetric. and you're going to bring them up against the heater plate. The heater plate is going to then start to bead up. You're going to see a melt bead all the way around that pipe. Once you know you see that melt bead first coming up, then you can reduce the pressure, the interfacial pressure of holding those ends together, and you want no interfacial pressure during that heat soak. Now you're just putting all that heat into the polyethylene and melting it back to a certain point, several thousandths of an inch back in there over this whole heat soak time, which is, again, a known value for the size of pipe that you're using. You're going to remove the heater plate. You're going to bring those molten ends back together now with a known and controlled, what we call interfacial fusion pressure. And that's going to be this part here. This is when that whole joint's being made. You're going to bring it together. You're going to get the rollback beads. And now that joint's done. Now what you have to do, though, is you have to hold that interfacial pressure during the cooling cycle to make sure that it doesn't move or get pulled apart while it's going from that molten phase to the solid phase and then cooling back down to a temperature that you can then take it out of the fusion machine and start moving it around. You can get this whole cycle recorded and uploaded to the cloud, where anybody in the world that has access to that cloud account can then go through and review all these to make sure they were done in real time every day before that piece of pipe gets buried. Really key aspect. Another thing that's unique to polyethylene pipe is squeeze off. People that haven't seen this before don't believe it. But I can guarantee you it is true, it works, and it's a great aspect of polyethylene pipe that can be taken into account. It was actually pioneered by the gas distribution industry into how they can squeeze off polyethylene gas distribution piping to do a tie-in or repair, and then open that pipe back up and the pipe's not damaged. And so you can do that with pipe today up to about 24-inch diameter is about the largest I think they have a squeeze-off tool for. And there's a guide for this, PPI TN 54, General Guidelines for Squeeze-Off of Polyethylene Pipe for Water, Oil, and Gas Applications. This is going to be different from gas distribution applications, which has some different types of caveats in it. But this, you go through this methodology, and this will make sure the pipe is not damaged. I'm not going to play the video here because it takes a while, but this is essentially what a squeeze-off tool looks like. It's a barred tool, barred on top and bottom with a very specifically designed radius. And then you squeeze off at a very specific squeeze rate, do your repair, and then you release that squeeze again at a very specific rate. That's going to be key in this process. So for example, within this document, TN54, it's going to tell you for every size pipe, what is the proper parameters for that. So let's look at 16-inch DR9, pretty heavy wall pipe. That's going to have an ID of 12.2 inches. Your squeeze rate, bringing those two bars together, is going to be 2 inches per minute is the recommended value. And it's going to take you 6.1 minutes to squeeze that pipe totally closed with a proper amount of wall compression. If you're below 32 degrees, that time's going to double. Now your squeeze off rate is only 1 inch per minute. You do your repair, put a tie-in in, whatever you need to do, and then you got to release that squeeze. You release it is going to be slower than the compression. That is very, very key. This is when the damage could possibly be done. And then you have to go very slow to make sure the pipe is not damaged on the ID during that release. So normal release time above 32 degrees will be 1 inch, or excuse me, ½ inch per minute, resulting in almost 25 minutes just the release time on that 16-inch pipe. If you're below 32 degrees, you got to double that again, and you're going to 1/4 inch per minute, up to 50 minutes or 49 minutes to release that squeeze to make sure that you don't damage it. All this is detailed within this document. If you follow those procedures, you're not going to have a damaged pipe, and it won't be an issue.
So if we didn't do that, Stephen, that area, water main breaks, of course, don't happen at 9 a.m. on a Monday after you've had your coffee. So they're 2 a.m. and one wants to get that water shut off. We just go back through and put a repair clamp around that at that time, right?
Oh, absolutely. Yeah. I mean, that's the thing too. You can just throw a repair clamp on it right then if you want. I mean, any repair clamp that you use on ductile iron or PVC, you can use that repair clamp on polyethylene to stop that leak immediately. And then you can use a squeeze off to cut that piece out later on and then repair it, give a permanent repair.
Okay, we've got quite a number of slides to go through, and right now it's at 3 o'clock. So we've got about another 15 minutes. I'll have to accelerate you a little bit there, Stephen. So
There we go. All right. Thanks for keeping me on track. Repair options. Another very good document to look at. So we get that question a lot. Well, I'd like to put polyethylene pipe, but what happens if it gets damaged? What happens if a backhoe hit it, or I need to repair it, or a directional drill hits it? So the Municipal Advisory Board put together this quick little document that kind of goes through and gives you a flow chart of what type of leak that I find or damage that I find. Is it a one hole puncture? Is it punctured both sides? Is it totally severed? What type of repair do I want to do? Mechanical fitting, electrofusion, and then it'll go through and just step you through the process. If you do this, I got to remove the pipe segment with butt fusion, install new segment with 2 electrofusion couplings. There's your repair option for this particular situation. So you don't have to know everything about it. It's going to step you through there and give you the most logical and reasonable repair option that's available to you. And you can see there's a multitude of repairs: electrofusion repair patch, electrofusion coupling to put a new pipe spool piece in there, or a flange adapter if you'd rather just go to a flange after that, or a fully mechanical coupling with full restraint pullout works just as well also. The same thing we just went through, trying to hurry up a little bit. Wait a minute, I think we're about done, aren't we? Where are we? So we talked about important resources such as AWWA, C906. AWWA C906 is polyethylene pressure pipe, 4-inch through 65-inch for polyethylene for water and wastewater systems.
You've got some case studies after this. This was just summarizing the resources.
Perfect. Here we go. Horizontal directional drilling. Polyethylene is the #1 material used for all HDD applications. It's not used for all of them, but it's the #1 used in about 65% of all HDD installs. It uses polyethylene pipes. F1962 is a great guide for how you design and utilize polyethylene pipe for these systems. Also, underground installation, if you take a look at that for sewers and other gravity flow applications, is ASTM D2322. So take a look at that also. Case studies. So nobody wants to be the first one to say, well, I don't know, polyethylene's this newfangled thing. It's only been around for 60 plus years. I don't want to be the first one to use it for this application. Well, I can assure you, you're not. And there's hundreds and hundreds of case studies. And again, polyethylene's been used as a pressure pipe for 60 plus years. So every application it has been used for, and there's case studies around all of those. The Alliance for PE Pipe has a great searchable database, which has over 350 case studies they pulled together just over the last, 7, 8, 9 years. So that's a great resource. You can go through and see, all right, has somebody used it for this? Has somebody used this size pipe for this particular type of application? You can go in and find all that within the PE Alliance website. As an example, you have, my screen's covered up here just a little bit. There we go. You have this canal conversion. We see this happening a lot in the West now. All the canals they have out there to bring water, irrigation water, or drinking water to these dry states have open canals. Well, they want to try to conserve that water as much as possible now. So they're converting the irrigation canals, open canals, to closed canals, and a lot of times using polyethylene pipe to do this. So this is a great example of the Ashley Upper Irrigation Company and the Highline Canal in Utah. They used 10,000 feet of 24-inch pipe, 26,000 feet of 30-inch, almost 60,000 feet of 36-inch, 48,000 feet of 48-inch for a total of 27 miles, almost 27 miles of polyethylene pipe to enclose this irrigation canal. So you can imagine all the different types of things they had to go through and they encompassed and encountered during that installation of this amazing system. Force mains. Again, we see polyethylene now becoming probably the #1 material for replacing failing force mains. That's probably the most rigorous application out there in the water and wastewater area because of the constant cycling of the pumps and the cyclic fatigue that these are going to go through. It's going to tear up a lot of different types of appurtenances and piping materials. Polyethylene, because of its surge capacity and ductility, is uniquely designed and capable of handling this. So we see polyethylene being used many, many times to replace these failing systems. This is Westminster, California force main replacement, 20,000 feet of 36-inch DR17. They ran dual lines of this to have a redundant system. We see it all over the country, this going on now for larger diameter force mains and polyethylene replacing that.
Oh yeah, Stephen, and then we didn't show it, but there's another job for low pressure force main in South Beach that was 4,500 feet of 54-inch. One of the things I'd like to point out specific to this picture that we're looking at is this contractor understood the paradigm shift in installing pipe and more production through opening up larger areas. So they went and rented more trench boxes. They've already disturbed the center island center median for this roadway. So they figured, let's just go ahead and get as much installed as possible. And they're starting to see that production run by installing more pipe all at once. So definitely a good way to do it. Glad you brought these ones up, Stephen.
Yeah, it's good. Like I said, fuse up large sections and pull them all into place all at one time and get them in there, do your backfill, and you're good to go. So there is some software out there too. I'm not going to get too much in depth on these, but these are great online tools to go to. You can just play with different scenarios and try to see, what type of design I need or different flow capacities, frictional losses for the HDP app calculator. Again, that's at www.hdpapp.com. I always wonder why they called it HDPE app, but I was told that it was designed like an app for your phone or your smart device, but it's not certified as an app. So it's a piece of software that resides at this address that works as an app, and you can use it on your phone or tablet as well through this website. PPI borate. It's a great first look tool at a directional drill job. It'll give you all the guidance you need to see what DR might I need, because that's going to kind of direct your application depending on how long you're going to be pulling that through, the depth of burial, and will this type of DR selection work for that, or do I need something heavier, or will something lighter actually work? Great tool for that. And then you also have the PPI PACE software. This is probably my favorite software because this goes through the pipe analysis and calculation environment developed by the University of Waterloo at www.ppipace.com. So that'll give you real world side-by-side comparison in a operating environment for ductile iron, PVC, and polyethylene to show you that what do you need to pick to get a comparable design off each material. It's going to be different. Their pressure classes mean different things. Their surge capacity is different for each material. Fatigue resistance is different, corrosion resistance, flow capabilities, frictional loss, all that's going to be different. So you put in your actual operating conditions and you can see how each material compares. So back on the HDPE app, this is what you're going to see. Click on the accept button. They're going to come up with very basic pipe information. Put in your size that pipe you have, 12-inch DR17, DIPS OD sizing. It's just give you basic information about it. Here's my outside diameter. Here's my pressure rating. Let's say it's 73 degrees. Here's a bunch of calculated values. Click on this more button, and you'll see a list of about 15 different types of values that's related just to that piece of pipe. Great place to go to, great resource. You can look at operating conditions. So let's look at the application. Let's click on pressure flow. What am I going to get with that? Well, let's say you have a piece of 8-inch IPS DR11. You got a mile of it. It's operating at 80 to 100 PSI, and I need to get 750 gallons per minute through that pipe. What's going to be my pressure drop needed, and at what velocity? Because those are two very key design aspects, right? So we know right off the bat, without even going to the software, that DR11 has a max pressure rating of 200 PSI at 73 degrees. It's also going to have 1.5 times that in your recurring surge capacity. That's up to 300 PSI. So 200 plus another 100 to give you 300 PSI surge capacity on everyday basis, 10 million cycles, 55 cycles a day for 100 years. And occasional surges, which is going to be a few million cycles over 100 years, at 400 PSI, double the pressure class or pressure rating. So we know that just off the bat. So you go to the HDPE app. Let's say I'm going to solve for frictional pressure loss. And I'm going to see, okay, at a mile of it, at 750 gallons per minute, I'm going to have a frictional loss of 37 PSI and a fluid velocity of 6.3 feet per second. That's well within the design window of polyethylene pipe. So you're not going to have any problems there. You can even go up to 12 feet per second with polyethylene pipe and not have any issues based on surge. Real key aspects. You can play with all these different ways of solving that. You can look at installation. You can look at unrestrained above ground applications. You can look at below ground applications. Again, because Alan's going to come on and yell at me for going too slow. But it talks about maximum pulling force for slip lining or above ground, anchor forces, suspension. What's my suspension a span that I need if I'm going across a bridge or something like that? Below ground, what's my pull force for slip lining, thrust block design, buckling pressures that I might need, earth loading, buoyancy, all that. You can go through those calculations and try different scenarios. Thermal expansion contraction. Polyethylene does have a higher thermal expansion coefficient. However, it's very easy to restrain because the force that it develops is very, very small. So with polyethylene pipe, let's say you got a piece of 200 feet of pipe and the delta T of 40 degrees Fahrenheit, you may get, theoretically, as much as 8-inch expansion from that. Well, to restrain that, it's only going to take 320 pounds to restrain that with. Whereas if you had carbon steel pipe, yeah, it may only move 3/4 or 3/5 of an inch, but it's going to take 8,000 pounds to restrain that piece of carbon steel pipe if you don't want it to move off that flange adapter or that valve that you may have in place. So again, you need to take all that into account with polyethylene.
So we've got 3 minutes left. I suggest you go to PPI pace and end it with that, if you wouldn't mind.
Yeah, let's get to that real quick.
It's slide 70.
Oh, there's a lot of earth loading here. Yeah, sorry about that.
No worries. It's all good stuff. I just talked too much at the beginning. My apologies, Stephen. Back to you.
Now, we talked about borate a little bit. I talked about all of these things. So this is just a slide of the borate calculation and what it tells you, what works and what doesn't. And here's the pace calculation. So let's say, that's like I mentioned here. So it talks about HDPE, ductile iron, and PVC. So you're going to pick the same sizes, 10-inch DIPS sizing system, pressure class 125, pressure class 350 for ductile iron, and pressure class 235 for PVC. Very common, very easy to use. So you can see all different pressure classes, but will they work in the application? Pipe length, velocity, recurring surge, occasional surge, working pressure 70 PSI, surges per day, 100-year design life. What's it going to take to get that? I'll give you examples about where all these numbers came from and support for that. It's going to show you how many surges per day. 55 is what all the design manuals recommend that you go with. That's not anything unusual. And then it's going to give you this output. It's going to say, all right, for these situations, well, my flow rate is all going to be comparable. My head loss is all going to be comparable. My total surge, that's where it's going to really start seeing some differences now, because ductile iron doesn't have the same surge capacity that polyethylene has. It has a flat 100 PSI. So make sure that's designed for, and it'll take that into, and you can take that into account. PVC has no surge capacity above the pressure class for everyday surges. It does have it for an occasional up to 1.6 times. So again, take that into account. Polyethylene has the 1.5 and 2 times surge capacity above its pressure class. So it's going to see, all right, do I have a 100-year design life on fatigue? And that's how your pipes are going to fail in these situations anyway. So you want a 100-year design life based on that. This gives you a real world comparison. And this is just the graphic output of the same information from the previous slide. Real world comparison on the different materials. Again, they all work if you design with them the right way, an appropriate way. What do you think, Alan?
Yeah, lots of different resources, and Stephen, your um, method. What's the word I'm trying to say? I'm flabbergasted. You covered it all. See, that's exactly what was
I'm
going on.
a little too wordy. Is that what it is?
No, no, no. You're very thorough, and that's the best way to be
Ah.
able to be when you're talking about resources in this manner. Because there's a lot of people out there that have lots of detailed questions. We got a lot of questions here
Good.
as well. If you go to the next slide, you'll see contact. And definitely, if you need to be able to get us, this is how you would do so. And then also at the end of this webinar is the survey, of course, for those PDHs, which we know everybody really wants. But I want to thank you very much, so Stephen, for being very thorough with all the resources, and then Don Lou for talking to us about real world problems and trying to solve water supply issues and needs for other people, and what the Engineers Without Borders continues to do.
Yeah, it was
So-
fun to hear from Don today. And
Yeah.
Stephen, I want to say thank you so much for putting this deck together. And sorry we didn't have enough time for it, but really great content. And, you know, honestly, we only lost a couple people through the end. So I think everybody appreciated it. And also, Alan, tell us about our webinar tomorrow.
Oh, tomorrow is going to be a classic webinar as well. That is HDPE versus PVC. So we've asked Dustin Langston to take it down just a notch to be able to help us with this, and he's very passionate about it. It's going to be pretty comprehensive, and we're very excited about it. Over 600 registrants for tomorrow. So that's quite a bit. And we had 60% yield today, Pete. That was probably a record for us for a while. So
Yeah,
I was
pretty good.
very
And
pleased.
Alan, please
Good.
remind us how to get our PDHs.
Stay on, and there'll be a survey at the end of this webinar, and you can complete which survey questions will make sure that you get right to your PDHs as you need them.
Good. Well, thanks so much, everybody. We'll sign off so you can fill out that form, and hopefully we'll see a bunch of you tomorrow. Till next time, we'll see you on the road.